So in lecture number 15 we will going to discuss speed control of a three-phase induction motor by changing the supply frequency. Now in our last class we have discussed changing of speed by changing the stator voltage, and now we are going to discuss the variable frequency control. And in this regard, in last class we also told you that by changing the frequency we can change the synchronous speed, because we know synchronous speed is directly proportional to the frequency. So synchronous speed is directly proportional to the frequency. So if we increase the frequency, so consequently the synchronous speed also increase. And in the same time we also mentioned you that by changing the frequency means if we increase the frequency we can increase the speed of the induction motor. And we have also mentioned that for this purpose we use VSI, voltage source inverter, CSI, current source inverter, and cyclo converter. And in that regard we have shown you this typical curve, that how that frequency changes the speed of the induction motor, and there we have depicted that as the speed is increasing, as the frequency is increasing, the speed is also increasing. Now we are going to discuss this a bit in detail. Now we have seen that this is my torque equation, this is my maximum torque, and this is the equation of starting torque, and this is the slip at maximum torque. Now in this equation, this x1 plus x2 dash term is always higher than r1 or r1 plus r2 dash, because we know that x equals to omega L, that is 2 pi fl. So it is always higher than this value of r1 or r1 plus r2 dash of the equivalent circuit. So we can easily neglect this r1 or r1 plus r2 dash in comparison with x1 plus x2 dash, and we will simplify this equation and we will see that what is the relation between this maximum torque, the starting torque, and the slip at maximum torque with the frequency. So if we see, so as this is much greater than resistances, so we have neglected that resistance term in the denominator, and if we simplify this we will get that starting torque is proportional to 1 by f cube. So starting torque is proportional to 1 by f cube, means starting torque is inversely proportional to the cube of the frequency. That means if frequency increases, the starting torque reduced very sharply. Now maximum torque, we have neglected the denominator in that r1 term and we have simplified it. So here it is v1 square. So again we can see, if we simplify the equation, it is becoming maximum torque is proportional to 1 by supply frequency square. So again we can conclude that if the frequency is increases, maximum torque also reduce drastically. Now again in case of slip, in the denominator we have again did the same thing, and we by simplification we got that slip at maximum frequency is proportional to 1 by f. That is, with the increase of frequency the slip is reduced. That means the speed for maximum torque increases. That means the speed for maximum torque increases. Now if we see this diagram, here the frequency has increases from f1 to f4, and this is a particular fan load TLA has been shown. Now from here if we can see that as the frequency has increases from f1 to f4, the load torque graph intersection point here, that is the intersection point with the corresponding torque speed characteristics shift to higher speed. So for f1 this is nr1. If we increase the frequency, the torque speed characteristics increases in higher speed, and in consequently if we go to f4, then we can see that nr4 value here which is very near to this synchronous speed ns4, and in the consequently we can see that as the frequency increases, previously the synchronous speed were here, now shifted to ns2, then shifted to ns3, and then shifted to ns4. So as the frequency increases, the speed has increases. But in this variable frequency control of the speed of the 3-phase induction motor has certain problem. Now what is that? Now consider the induction motor operating at low frequencies. So if it is operating at low frequencies, the motor impedance is low. The motor impedance is low, because if we see in the equation that x1 x2, right, so x1 is again omega L, that is 2 pi fl. That means reactance is directly proportional to the frequency. Now if the frequency is very low, this value of reactance is also very low, so impedance is also very low. Now thus for a constant voltage the motor current become higher, because rotor current I2 equals to voltage, or rather we can say induced voltage, divided by the impedance of the rotor circuit. So impedance, as the impedance is very low, so current is also very low. That means the I square R loss, copper loss, will increase. Secondly we know that E1, that is the induced EMF, is equals to 4.44 phi f k ts. Now 4.44 k, that is winding factor, t, that is number of turns, is constant. That is induced EMF is proportional to product of flux and frequency. Now we know if we neglect that stator drop, that is I1 into R1 plus jx1, we can say V1 is closely proportional to E1, that is the induced EMF in the stator. Now V1 is the supply voltage, so it is constant, so you can say E1 is also constant. And just few minutes back we have told you that induced EMF is proportional to the product of the flux and frequency. Now to keep the induced EMF remain constant, if the frequency reduce, that means the value of flux has to increase. That means the core will become saturated, and which in turn will increase the core losses. So we can see at lower frequency level the copper loss is also increasing, the core loss is also increasing. So it will reduce the overall efficiency of the motor. Now what happens if the frequency increases? Now again we know that induced EMF is proportional to product of phi f. So if frequency is increasing, then to keep the EMF constant, that is E constant, the phi has to decrease, and this is known as flux weakening effect. Now due to this effect at higher frequency, the developed torque, the starting torque, the maximum torque, all of this reduced substantial amount, and it may so happen that at higher frequency the starting torque is such a low value that it cannot meet the requirement of the load torque. So the motor will start stalling. So the motor will start stalling. Now this can be depicted if we see in this figure. Now what we have done in higher frequencies, right? That means here the most higher frequency is F4. Now if we see, the torque line is now TLV. So if we see, the torque line is this, and this is my torque speed characteristics, and there is no intersection point between this developed torque and the load torque. So at this condition the motor will stall. So this is the details of variable frequency control of induction motor to control the speed. Okay, so this is all about today's class. Next day we will start V by F control, that is variable voltage, variable frequency control. Thank you.